afternoon everyone. So, in today's and the next lecture I am going to introduce yet another new transform, that is the wavelet transform. Now, the introduction of wavelets interestingly was not done by any mathematician, but engineers, and this is one prime example of a transform that came into existence not because of the theoretical requirement, but because of the practical applications, the practical needs of solving certain problems in domains of engineering and science. So, wavelets has, without emphasizing the importance of wavelets, I just want to say that wavelets have revolutionized many areas of science and engineering, starting from biomedical, medicine, signal processing, and I mean the students should always find an application. I mean, you name an area and wavelets are there. So, let me start the discussion on wavelet transform. So, before that, again I just want to briefly emphasize the applications of wavelets. So, the applications of wavelets are manifold, starting from areas in signal processing, from signal processing to astrophysics, to digital communications, to let us say image processing or pattern recognition, even in approximation theory, in quantum mechanics, in optics, in you can see that there is a list of areas where wavelets are widely and the use of wavelets are widespread. So, biomedical engineering. So, these are some of the applications that I can think of, sampling theory or statistics. So, sampling theory, matrix theory, right. So, matrix theory, statistics, petroleum engineering. Well, especially the use of wavelets are used in petroleum engineering to record the segmentation of well logs. So, we see that the applications continue. Okay. So, the wavelets, as we see, the wavelets are widespread in almost any areas that in science and engineering that we all can think of, and let me just highlight that the start of all these, the applications of wavelets started as late as in 1980s, moving on to 90s and 2000s. So, let me just start our discussion by just briefly mentioning what are these wavelets. So, wavelets, well, as the name suggests, wavelet is a short wave like pulse. Okay. So, these are short wave like oscillations or pulses. Okay. So, these are the building blocks of the transform. Okay. So, when we construct the wavelet transforms, it is all about a reasonable integration using these wavelets. Okay. So, let me continue by showing you some of the development in this area, and then we are going to discuss during the course of our lecture, we are going to discuss some of these recent developments and in the form of results and theorems. So, the start of wavelets was, as I said, was in 80s, and that is again via some engineers, some geophysical engineers. So, interestingly, it was not brought about by any mathematicians, but engineers. So, the first person in this list of record is in 82 by Jean Morlet. Morlet was a geophysical engineer. His idea, along with Alex Grossman Alex Grossman, who was a theoretical physicist, was the start of this area. So, the area started with the initial ideas put forward by these two scientists. So, then so they introduced, so that is the first start. So, they introduced the idea of wavelets, using wavelets to describe complex engineering processes. So, then the next major development was in 85, where a pure mathematician by the name of Yves Meyer. So, Yves Meyer saw the relation between wavelets and harmonic analysis. So, this scientist was able to identify the relation between how this wavelet influences certain areas of harmonic analysis. Okay, so, established connection between harmonic analysis and the Morlet algorithm, that was introduced by Jean Morlet earlier. Okay. So, then there were several other developments which I am not going to go into great details, but I am going to highlight some of the major milestones. Between 85 to 88, there were certain work by these three people, Meyer and Lemery. So, these are all French scientists, and Mallet. They introduced the concept of orthonormal wavelets. Okay. We will also see in our discussion as to how to construct orthonormal wavelets. Okay. And then another big achievement was in 88 by a Belgian mathematician by the name of Daubetschis. So, Daubetschy introduced the so called Daubetschy wavelets, which are orthogonal wavelets of any given prescribed order of continuity or order of differentiability. So, these were special orthogonal wavelets with prescribed degree of smoothness, Okay. So, this was one of later on in my second lecture I will highlight some of the wavelets that were developed by Daubetschis, namely the orthonormal wavelets of the second and the fourth kind. So, then so these were some of the major milestones. Let me just highlight briefly some of the other milestones. Well, it was seen, although lot of work was done in the early 80s to late 80s, but it was seen that despite all this development, it was seen that it is very difficult to construct symmetric and orthogonal wavelets. So, symmetric, so some work was done in the early 90s on that area. So, it was seen that it is difficult to construct symmetric orthogonal wavelets, orthogonal compactly supported wavelets. So, when I am going to use the word, whenever I use the word support, by support I mean a subdomain where the wavelets are defined. So, when I say compactly supported, this means that the wavelets are defined in a particular subdomain of the real or the complex plane. Okay. So, then some work that was done in this area were by Cohen in 92. He did some initial work on biorthogonal wavelets. Okay. And then Chui and Wang also introduced, so that was all done in the early 90s. these two scientists introduced the spline wavelets, which were semi-orthogonal wavelets. So, spline wavelets or semi-orthogonal wavelets. Okay. And then another notable mention was by Belkin, a Russian scientist, and Kaufman. So, they introduced in 91, they introduced the multi-resolution wavelets. So, we are also going to study one particular case of multi-resolution wavelets, namely the Dobeci wavelets. Okay, so as far as the major developments are concerned, so these were some of the major milestones. Well, the work continues in this area, and I am just going to highlight some of the development, the early development, followed by some of the major results, and also later on I am going to introduce the Dobeci wavelets. Okay, so moving on, let me just start with the definition of the wavelet and also introduce the concept of wavelets. So, I am going to start with the continuous wavelets. The discrete wavelet will follow sometime later in this lecture. So, continuous wavelet transforms. Okay. So, what I have is, suppose now, so far we have seen different types of integral transforms. I have seen that integral transforms are to be defined by the following operator T of f y, which is defined by an integration over certain specified domain of k times some function k of x y times f of x dx. So, k of x y, we call this particular function as my kernel of the integration domain. Okay, so then, well, we have seen different types of kernels in our discussions of different transforms. In particular, if suppose my kernel is the following trig function, so it is e to the power x times y, or let me write it in another way, this is e to the power minus x times y, right. So, I know that this is the case of my Fourier transform. So, this has already been discussed in great detail, right. So, let me call this particular function as phi of y. So, phi of y of x, right. So, what it means is that as if y is like a scaling factor to this function e to the power I x. Okay. So, my y is a scaling factor, it is a scaling factor to this function e to the power I x. Okay. So, we see that for this particular transform we have this following kernel. Now, in the case of wavelets, we are given the complete independence of describing the kernel, which means that depending on specific types of wavelets that we choose, our kernel is going to vary on a case by case basis. So, let me start with a general function which is square integrable, and I am going to describe how to construct wavelet transform. So, let us say I am given, consider any function psi such that psi is square integrable over R. So, what it means is that the following integration of psi square dx is finite. Okay. So, psi square integrable. Okay. So, then let us consider a scaled version of this function. So, a scaled function, let me denote it by psi of a b of x. So, now psi of a b of x is defined as 1 by the scaling factor. So, 1 by a to the power 1 half times psi of x minus b by a. x minus b by a. So, where I have that a is my scaling parameter and b is my shifting parameter. Okay. So, I have scaled and I have shifted my function by the respective constants a and b. Okay. So, then under suitable conditions, which I am going to describe slightly later, I can always define my wavelet transform as follows. So, I am going to say, so let me just introduce the definition of wavelet transform. So, by continuous wavelet transform, I have that psi of a b, well, so psi has already been defined, but the wavelet transform I denoted by this capital W. So, W, the transform with respect to the function psi of the function f is denoted by this following integral from negative infinity to infinity of f of t times psi bar a comma b of t dt. Okay. So, if I am given a suitable function which is square integrable and plus some other condition, I can always define my continuous wavelet transform by this definition 1. Okay. So, now in this case, this function psi, note that I have taken a conjugate of this function psi. So, in general psi can be a complex function and we can take conjugate. Okay. So, then before moving ahead, this psi is known as the mother wavelet. So, the psi is the mother wavelet, or it is also called the analyzing wavelets. Okay. So, psi is also called the mother wavelet or the analyzing wavelet. So, this question is the first question that arose in this definition is, what are the suitable values or what are the suitable functions psi that can be used to describe my continuous wavelet transform. So, which means for a given, so this question is for a given psi is one defined. Okay. So, for a given psi is one defined, the one means the definition of the wavelet that I just described, is it defined. Now, or an equivalent question to be asked is, can my function f be reconstructed from my wavelets, from my wavelet functions psi of a of b. Okay. So, namely, can the inverse be suitably found so that I get back my original function. So, to answer that question, I have to introduce another definition. So, let me introduce a definition of the wavelets. Okay. So, it turns out that not all functions are going to be considered in my definition of the wavelet transform. It is only these particular functions that I describe now will be considered. So, for a wavelet, we mean a function psi which is all square integrable such that this following integral of psi hat by omega. So, where this hat denotes the Fourier transform of this mother wavelet. So, the Fourier transform square by the transform variable, the integration of this quantity is finite. Okay. So, by wavelet I mean all those square integrable function such that this particular integration is finite, where, as I said, where my psi hat of omega is 1 by square root 2 pi integral minus infinity to infinity e to the power negative I omega x psi of x dx. Okay. So, that is my Fourier transform of the wavelet, the wavelet function. Okay, so notice the following. Students are requested to check that the square integration of this. So, if I am given that the wavelet function is square integrable, well, square integrable, it also means that the scaled and the shifted version of the function is also square integrable. So, that can be easily checked, So, what I mean to say is that the L2 norm of this function is, students can check, this is also equal to the L2 norm of the scaled version of this function. Okay. So, these two norms are equal in the L2 sense, in the square integrable sense. Okay. So, then so notice that my Fourier transform, the Fourier transform of the wavelet can be found, the Fourier transform of psi a comma b of x can be found to show that this is, we see that the Fourier transform of psi a comma b of omega psi hat is 1 by a to the power 1 half of 1 by square root 2 pi integral negative infinity to infinity e to the power negative I omega x of psi of this scaled function x minus a by b dx. We see that the Fourier transform of the wavelet can be evaluated by this integral, okay, of the scaled wavelet. Okay. So, then if I were to evaluate this, I see that, well, let me just continue to post process. Let me call this expression by 2. So, if I were to evaluate this expression, so let me substitute another variable t by this scaled and shifted variable. So, choose my new variable t to be x minus a by b. I see that my integration is as follows: psi hat of a comma b of omega is 1 by a to the power half 1 by square root 2 pi integral negative infinity to infinity, and I get this is also, well, I get that this is the following e to the power, well, let me write down the final expression, students can continue. So, I get e to the power I omega x of psi of t and then dt times some factor which will come out of this scaling result. Okay. So, after all the simplification, let me write down the final expression. I get that this transform of this scaled function is this particular factor times the transform of the original function. Okay. Okay. So, we are going to use all these results when we show some specific examples of wavelets. So, let me start with the first example. So, the first example that I want to show is the famous Haar wavelets. So, Haar wavelets are step functions. Okay. So, which means the wavelets are described by the following values. These are 1 when x is from 0 to half, and these are minus 1 when x is from half to 1 and this is 0 otherwise. Okay. So, these are my wavelet functions values, and if you were to draw this function, I see that this is psi of x by x. Okay. I see that if I were to draw this is also the following value. Well, I see that there is a step function and the step is at x equal to half. Okay. So, at half there is a sudden jump from value 1 to negative 1. So, that is my Haar wavelet. Okay. So, if I were to, so consider now, let us see what is the Fourier transform of this Haar wavelet. Okay. So, the Fourier transform of psi So, that will be denoted by psi hat of omega. Let me call this as, well, this is also denoted by the transform of psi of x, and this is, so if I were to evaluate the transform, let me just evaluate and give you the final expression of this transform. This comes out to be 1 by square root 2 pi in times sines of omega by 4 whole square divided by omega by 4 times e to the power negative omega minus pi by 2. Okay, so I see that if I were to further simplify this expression, I see that this is also 1 by square root 2 pi 4 I by omega e to the power negative I omega by 2 sine square omega by 4. Okay. So, then let us now check what is the square integration of psi hat square divided by omega to see whether this is indeed a wavelet or not. So, let us check what is. So, students are asked to check this following integral. So, check this integral from negative infinity to infinity of psi hat omega divided by omega, this the transformed function square divided by the transform variable. If we were to integrate this, in the case of har, I get the following integral. This is integral 8 by pi from negative infinity to infinity sine of omega by 4 whole to the power 4 divided, well, this is in terms of the absolute value, divided by mod omega square d omega, and then it is easy to see that the numerator is bounded, the denominator for larger and larger values of omega becomes bigger and bigger. So, this integration is finite. Okay. So, I see that this psi square in the asymptotic limit, my psi hat is proportional to 1 by omega. We see that in this limit, in the limit when omega goes to infinity for large values of omega, I see that psi hat is proportional to 1 by omega. Okay. Now, if I were to draw this transform, let me just show you how this transform looks like. The transform of the absolute value of the transform of psi, the wavelet, the Haar wavelet versus the transformed parameter. I see that the wavelet has a discontinuity, well, has a first order discontinuity at 0, and I see that of course the wavelet will be symmetric, and so this is the type of what the transform looks like. Now, notice that the decay of this wavelet in the transformed plane is of the order of 1 by omega. So, the decay rate that I mentioned is of the order 1 by omega. So, in wavelet theory, this is a very slow decay. Now, typically we want that the decay of the wavelet for large values of this transform variable, or well, so for the large values of omega, the decay should be faster, should be very fast. Okay. So, in that sense the decay is very slow for the Haar wavelet, and the reason is that there is a discontinuity in the original wavelet transform. Okay. So, there is a discontinuity. Due to discontinuity, I see that the decay rate is relatively slow in the transformed plane, and that is considered a weakness in the transform. So, later on I will show you a special case of a transform, that is the Dobeci transform, where I can remove this weakness by assuming as many derivatives to vanish to 0 as I want to construct. Okay. So, that is the degree of freedom that particular wavelet has. Okay. So, then